So I thought I should probably just do some exercises before I start like not remembering any of this. Why did this happen? Yeah, that's better. So here we are. It's this book actually provides us with exercises, and it's like, yeah, lots of exercises. So there's 50 something questions. I don't know. So it will be good. Like we'll get enough practice. I don't know. It should take like an hour or something. If I solve it at the speed that I was capable of at one point in my life, it would have took just an hour. Now it might take like 2 or 3 hours, but let's go. So first question: the following are the state diagrams of 2D FAs M1 M2. Answer the following questions. What is the start state? Come on, just Q1, and that's it's Q1. What is the set of accept states? So the capital F, that's Q2 over here, and that's Q1 Q4. What sequence of states does the machine go through on input AABB? So this one, well, A just pushes it to Q2, then you have A again. Oh, it's A or B, right? So it goes to Q3, then it's supposed to be B. B takes it to Q1, and then Q1 again. So it goes back to Q1. So it doesn't accept the string. What about this one? Well, A, then A again, and then it does B. So it goes to Q2, and then it goes to Q4. So it accepts it because Q4 is an accept state. So does the machine accept the string AABB? Well, M1 doesn't, M2 does. Does the machine accept the string epsilon? So Q1 is not a accept state, so it cannot accept epsilon. But over here Q1 is. So yeah, M2 does accept epsilon. Next, give the formal description of the machines M1, M2 as in exercise 1. So I should just do this. So first is like done, everything. The second one, give the formal description. The M1 is once again, oh god, this is going to be hard. So first you want the capital Q thing, so the set of all states, which is, or you know what, I'm just gonna write down what the sets actually are rather than, yeah. So our capital Q is this thing, Q1, Q2, Q3, right? What's the start state? That's Q1, so there's only one state for a DFA. What's the finishing states? That is the accept states. That's only Q2 in there. What's the delta function? Well, delta function is going to be complicated. I mean, you see it as like graphs and everything, but right, it's going to be complicated. So once again, delta, by the way, goes from and I should probably tell you what sigma is, right? Oh, that is just A and B, I guess, because there's no other character that we used anywhere on this graph. So I'm assuming it's just AB, right? Then what's delta? Delta is this table basically. It's a function, but we're giving it as a table. So once again, delta goes from this sigma cross the state to another state in a DFA. In an NFA, it goes to the set of states or something. So right, on this side I'll just put the characters, so it's A or B. Over here I'll put the different states, which are Q1, Q2, Q3, and I'll just do this M1 thing, and I won't do it for M2 because that's a lot more complicated and it's just wastes time, right? Okay, so what happens when your machine is at Q1 and you encounter A? Well, it goes to Q2, right? Yeah. If it's B, it goes back to Q1. Then if it's at Q2 and it encounters A or B, it goes to Q3. So in both cases it goes to Q3. And if it's at Q3, if it encounters A, it goes to Q2, and if it encounters B, it goes to Q1. So that's the delta function, right? And yeah, that's the formal description. That's it. The M2 thing is also like very similar. We won't be doing that. Next question. Third, my handwriting has got much worse. The formal description of a DFA M is this thing, where delta is given by, okay, give the state diagram for the machine. So you have 5 states, Q1, Q2, Q3, Q4, Q5. Though only 2 characters, U and D. There's a delta function given. There's the start state Q3, and there's the final state, which is also Q3. So Q3 is, I should write like that. Wait, I'm using it incorrectly. Yeah, that's better. I'm really just Wow. Yeah, out of practice with this stuff. So this is Q3, and it's also the final state. So delta is something like this. For oh, so this is how the table should have been. I just transposed it. Well, whatever. So let's see. If it's a Q1, it goes back to Q1. I'm just gonna start drawing up stuff. So I'm just gonna draw like some circles. And how many states are there? Well, there are 5, right? So there are going to be 4 more circles. So let's just say this thing is Q1, right? So with U, it goes back to Q1. So there's this arrow. Then with D, it goes to Q2, which I'll just say it's this thing. So this is like with D. Okay, that's what Q1. Then for Q2, with U, it goes to Q1. So with U, right? With D, it goes to Q3, which is this state. So this is for D, right? Where was I? Right. Then you have Q3. So with U, oh, so it's like, oh, so it's kind of weird, but I think by U and D, they probably like are short for up and down. As in, look, one is the upmost thing if you think of it like that. Well, with U, you can only go up. As in, 2 becomes 1, 3 becomes 2, 4 becomes right. I get it. It's a pretty simple kind of graph in that case. It's got Q1, Q2, Q3, Q4. Right, these are all the states. With U, this guy just goes like to itself back because it can't go up anymore. Well, each of these with up, they go up. Pretty, like, literally they just go up. And then with down, these go down. And then Q3 also happens to be the final state, so just double circled. So yeah, that's the state diagram. Just resize it because I don't want this. Fourth, okay, fourth is each of the following languages is the intersection of two simpler languages. In each part, construct DFA for the simpler languages, then combine using the construction discussed in footnote 3, page 46 to give the state diagram of a DFA. So these are the intersection of two languages, right? Yeah. Oh, I think we did union. We also did all of that. The intersection is slightly tougher, isn't it? Okay, so how do I do this? Right, so what we'll essentially do is that we'll just suppose you have machine 1 and machine 2, and you want the intersection of the language of machine 1 and language of machine 2 to be the language of whatever we are creating. What we would essentially want is that that once you input the language, and then let's just say these two are running parallelly, if both of these end, right, if both of these go to the final state, then you're done, right? So whatever like final state you will have over there, these with epsilon arrows will just be like, or should I even use epsilon arrows? You want what? You want a DFA? Oh, that's kind of tough, but okay, this is also doable. So then our F set would just be F1 cross F2. As in, if this is at a final state and this is also at a final state, well, then the whole machine is at a final state. Once again, our Q will just be Q1. So let's get rid of this diagram and just do this thing. So I'm going to tell you how to do this thing. Capital Q is just Q1 cross Q2, right? Yeah. So first machine is in some state, second machine is in some state. Combine these two entities together to give the state for the whole machine. Then your capital F will also be F1 cross F2. Your delta function, that will be going, once again you just take in some input, and now you have this set Q1 cross Q2 as your new Q, so I'm just going to call it Q, and that gives something in Q because it's a DFA Indian. So the delta function works like this. Suppose delta 1 and delta 2 were the transition functions of the the two machines. What? Okay, we don't want this stuff. What is this? Come on. Oh, this won't go away, huh? Fine. So suppose delta 1 and delta 2 were the two transition functions. What we want is that, okay, so the first machine is at state 1 and second machine is at some other state. So it's like Q1, Q2, whatever. Suppose Q1, Q2 are in fact the states. Then what you want is that delta of Q1 cross Q2, that should just give us delta 1 of q1 cross delta 2 of q2. That's better. So that's how the transition function will work, right? Am I missing something? The alphabet. So suppose these have different alphabets, like alpha 1, sorry, sigma 1, sigma 2. Well, they're also having the same alphabet, sigma 1 union sigma 2, because like they accept that alphabet, right? So you can just always combine it, and we'll just assume that these are the same from the get-go. Cool. Missing something? No. It's a five tuple, right? So you got capital Q. Oh, the initial state. So the initial state will just be, just call it Q naught. I shouldn't call it Q naught. Whatever, just call it Q. That will be, you know, the. This is kind of weird. Oof. Yeah, so just like Q naught, this is like Q naught 1, Q naught 2 or something, you know. But it's this tuple actually. Yeah, that's thing. And this also should be a tuple. Sorry, I'm just like messing around. So for NFA it would be a cross. For a DFA it's just a tuple. Right. Okay, so we want to construct a DFA for each of these languages. Right, so first A is W such that W has at least 3 A's and at least 2 B's. Wait, that's it? That's all you want? Okay, so you can think of it as being the intersection of a language where you have 3 A's at least and another language where you have 2 B's at least. So you first, like, let's just build something that has 3 A's. How do you do that? So you have this start state, just say Q naught and Q1. So every single A it will like progress. So first A it consumes to get to Q1, second A, and then third A to get to Q3, and this is the final state. Now what happens during B? Well, it does not progress. So it just goes back. B, B, B like that, and B like that. So that's the first machine, M1. Yeah, you can write the formal description of this whole thing. I'm not going to do any of it. I'm just going to show you like it can be done, right? Then once again it has at least 2 B's. Come on, seriously. So the same stuff, Q naught with B, Q1. Oh right, and this probably we should I mean, what happens if this like encounters A? So it should go back in both cases. It should go back in A and as well B. Yeah, that's how it should be. Okay, so then with 2 B's it gets the final state, which is, let's just say Q2, and now it doesn't matter what happens, it just is there. Right, so this is M2. Now how do you combine M1 and M2? Like this, of course. Yeah, right. Should I actually like write down a whole new machine which, you know, does all of that? I don't think so. I don't think so. Anyway, so this new like capital Q, how many states would be there? It's going to be 4 cross 3, I guess. Yeah, so that's going to be 12 states in there, which is a lot to draw, so I'm not going to do that. Okay. What is this A thing? I don't know. So once again, W such that W has exactly 2 A's and at least 2 B's. Okay, exactly 2 A's. So like, let's just consider M1, right? If your M1 was something like this, then it would be at least 2 A's, right? Now you want it to be exactly 2 A's, so you don't want whenever you will encounter A, it's just that this goes back. No, oh, you know what? Actually, let's do this thing. So what we will actually do is instead of making this the final state, we'll make this the final state, right? So that with 2 A's you progress with this, but if you take any more A's, you go to Q3, and Q3 is not a final state, so you'll just like get rejected. So that's W1, so that's M1, and then once again at least 2B, so that's M2 once again. So then, like, yeah, combine these to give the intersection. And similarly, C is, W has an even number of A's. So for an even number of A's, I think I got it. So it's like, it's supposed to be some kind of cycle. So let's just say q1 is the initial state. So with 0 is also like the thing, right? So you just have to have two A's to come back. So there's only going to be two states. This is the initial state, and then you over here as well, this is the initial state and this is the initial state. Cool. So I'm talking about C. First you just have W has an even number of A's. So for the machine for that is something like this. And then what happens with B? Well, with B you just don't progress. Oh, no, actually, yeah, this is how it should be. Cool. And 1 or 2 B's. So you want like less than that. So the complement of the whole machine, something like that. Right. 1 or 2 B's. How do you do that though? You want the complement of this. Hey, so how do you like make the complement of a DFA? So this is the accept state, right? It is for at least 2 B's. This should probably be a reject state in that case. Although rejected state doesn't actually make sense, but well, whatever. So then this would be the case, right? So with 0 B's you are like done, because this, wait, oh, so you just want 1 or 2. You do not want, okay, I get it. So this is going to be a slightly different machine. So let's just leave it and let's just draw it new over here. It's Q0, this is Q1, this is Q2, and we'll draw final third state Q3. With each B it progresses. Now you want only stop at 1 and 2, so this will be the thing and this will be the thing. And once again the same whole stuff, like with A it loops back, and this loops back with both A and B. Cool. Right, so this is the machine. So notice that only with 1B or 2B do you get to a final state. With 3B you suddenly get to Q3, but that's not a final state. Cool. And of course you start over here. So just combine these somehow. Oh, this is getting boring really. Then W has an even number of A's, done. Each A is followed by at least 1B. So getting to regular expressions. Okay. So you already got like W has an even number of A's. That's like deal. Hey, I think you don't even need to draw two machines. You can draw it in a single machine, but we'll still do it. So then you want that each A should be followed by 1B at least. So suppose there is no A, then well, you're done, right? You don't need to do anything. So if you are, whatever your initial state is, if there's like no B, if there's no A, you're done. So that should also be a final state. And with each B, you're just supposed to loop back. So even the epsilon string would be working for this language. So with B's, you just loop back. Now with A, you have some kind of conditional, so I'm going to make it go to another state, and it should be following a B to get back. So with a B, you can do that. Right. Now what happens if you encounter another A somehow? Then let's just make it go to a reject state. So it's Q3. So once again, with A, with B, there's a DFA in the end. We have to like tell everything that happens. Cool. And Q3, well, it just stays there. Doesn't matter what input you put, like it just stays there. Cool. Yeah, and sometimes I guess it's just better to not draw this. I don't know. I'm just still going to draw this. Yeah. So this looks like the machine that we're talking about. So if you ever encounter A, you have to encounter B immediately next time. Otherwise, if you encounter another A, you are done. You won't ever get to Q1, right? So that's A is followed by at least 1B. Then W starts with an A and has at most 1B. Oh, so that's the machine that I was talking about previously. So this is like at least 2 B's, right, to get there. So what's the complement of at least 2 B's? At most 1 B, right? So all you have to do is just swap the reject and accept states, as in every input where this would have been rejected is now the input where it's accepted. and every input where it would have been accepted is where it would have been rejected. Cool. And everything else stays the same, I guess. So that's the complement of a machine or of a language, right? So this machine would just have like at most one or two, sorry, at most one B, right? Yeah, it starts with an A. Oh, come on. So if it, that's actually pretty easy, right? You just have a state, and if it's, well, starts with an A. Yeah, so if it ever encounters a B before you encounter the A, it just like gets trashed to some state where, you know, it's a reject state and this is the accept state. So now it doesn't matter what happens, we are good. Doesn't matter what happens, you are bad. And this is where you start, of course. Something like that. Okay. W has an odd number of A's and ends with a B. Okay, so I'm getting bored by this whole thing. Let's go to the next one. Oof, once again. So now you want to construct a DFA for the simple languages, then use it to state. So it's the complement of simpler languages, right? So for example, this one W does not contain the substring A, B. This would be that W must contain, the complement of that is that W must contain the string A, B. That is, you must have one A followed by a B, right? Yeah. So if you ever encounter one A followed by a B, you immediately get sent to the final state and you're done. Like you just stay there. What if it doesn't? Well, then you go back to whatever you were doing. So let's just like make this machine. So you start off with something, right? Then what must happen is you must be having an A to progress, right, to another state, Q1, and then you must encounter B to progress to the final state, Q2. But what happens if you like you get an A but now you get another A? Well, in the end you are still stuck at A, right? You need another B, so you just loop back. In the case of an A, with B you go there, and like with AB you just go back to the final state. It doesn't matter what you do at that point. And what happens with a B for Q0? Well, you just get back to this because you have never encountered an A, so that's kind of problematic, right? So that's the machine in which you contain the string AB. So now you want a W where you do not contain the string AB. So you just take the complement of this by switching out all of these except for reject, and yeah. Oh, this wasn't an accept state from the get-go. So this is the machine that we're talking about. Now you will change it. So now these two will be accept states and this will be a reject state. Cool. I'm saying reject state, but there is nothing like that in reality. But you get it. Yeah. So if this machine ever does encounter AB, you know it's gonna go to Q2, but Q2 is not an accept state, and it's gonna stay there, right? So yeah. So this should be easy. This whole thing should be easy. Okay, there's some regular expression stuff going on. So W is a string not in A star, B star. So first you need to find a machine that has W, which is a string. So it accepts all W which are strings in A star, B star. As in A star, B star is the language. And then you just have to take the complement of that. So A star would be like any number of A's, and then you have any number of B's, and then you're done, right? So you just have like some initial state, you need a bunch of A's, then you need a bunch of B's, right? There should be at least one A, right? But what if you have epsilon A's? Well, then that's slightly complicated. That's complicated. This one is actually kind of complicated, isn't it? It's sort of like the concatenation of two things. Like first you should just have like some A star stuff. You should have B. Right, so if you ever go to the B region, like if you encounter a B, even like from the get, so first doesn't matter how many A's you have. So with every A, just get back to the initial state, right? Like you could put in as many A's as you want, but the moment you encounter B, you cannot ever encounter an A again. So with B, you progress to the next stage, where if you ever encounter an A, you get thrashed to a reject state, which I'll call Q2. And let's just say that this is actually the accept state, right? So it doesn't matter how many B's you encounter, you will stay there. I guess that makes sense. Oh, this probably should also be an accept state. So like, before you encounter a B, it's still a valid string, right? Because it's B star, you could also have epsilon. So yeah, this would be the thing. Then the complement of that would just be like, don't make these the accept states, make this the accept state, right? That's the complement of the language A star B star. Cool. Then you have W is any string not. So yeah, we are done. This is just getting too much. Too many like weak questions. So by the way, B plus just means like, it just means this thing, B concatenated with B star. Sorry, B star, not B plus. And that whole thing starred, and oh yeah, by the way, the string starred is just the string concatenated with itself any number of times, including 0 number of times, which means the empty string. Yeah. Anyway, so that's it. We won't be doing any more of these weird questions. I guess we got enough practice on constructing DFAs. So 4th and 5th, I guess we are done. 4th is that. 5th is like just let's like convert. So just accept to reject. It's converted to reject states, and vice versa. Cool. I shouldn't be drawing it like this. It seems like a bijection. This is better. Accept becomes reject, reject becomes accept. Then 6th question is, give state diagrams of, once again, in all parts the alphabet is 0, 1. Fine. So W begins with a 1, ends with whatever all of that stuff is. A, yeah, just like miscellaneous questions. You don't even, oof, fine. Okay, so you want, it contains a particular substring, right? Or some X and some Y. So how do you deal with these substring questions though? I guess you just make like bunch of states. So suppose you have a substring like A, B, C, D out of some alphabet, I don't know. What do you do? Like, and you could have anything over there. So, right, you just have some initial state, and with all kinds of alphabets, you like don't really care what happens. So everything, the whole sigma thing, except the A thing, right? So with A though, you progress to the next state. Then similarly with B, you progress to the next state, but with everything else, you just go to, you go back to the basics, sort of. Like you need that particular sequence, and anyway that the sequence breaks, you just like go back to the starting, something like that, right? Because now it's broken. It won't work, so you just have to start again. I guess that's how you do it. Fine. Cool. So you can draw state diagram for this stuff, I guess. W has length at least and, so whenever you encounter an and, it's an intersection, so you just have to make two machines, combine them with the intersection method. Yeah. And whenever it's an or, it's a union. So how do you make the union of two languages? Well, so over here it was like, it was basically this thing. You're gonna do the same thing, except that your accept states are not F1 cross F2 anymore. So 6th you can pretty much do it, but this is like containing an or over there. I'm just gonna like do it with the union first. So once again, it's all of the same stuff as in 4th, copy paste, except that your F is not the same. Your F is a different thing now. So it's not F1 cross F2, it's like or. So you could have anything for the any state for the second machine, but if the first machine is at a final state, well, we are done. And similarly, so like this whole thing, and similarly you could also have anything for the first machine, but if the second machine is at a final state, you are done. So this, by the way, also contains F1 cross F2, but it's bigger than that. So this is your set of final states, right, for a union. So that's like this whole thing is for union. Cool. Okay, next. So you got an and, you got an or, you understand all of that, right? Okay, then W doesn't contain the substring 110. Or sorry, all W such that W doesn't contain a substring 110. That's a complement. That's a complement of W does contain the string 110. So you can draw for that. Like, it's pretty easy. And then you just have to change the accept and reject states. Then the length of W is at most 5. So once again, it's like at least 5. So it doesn't matter what alphabet you have, we just progress to the next state if it's an alphabet. So let's just draw something that, yeah, I guess this will work. So it's at most 5, right? So with 0 things in it, it works. With 1 things in it, it works. With 2 things, it works. With, so this is like 0, 1, 2, 3, then 4, and finally 5. So with 0 characters in the string, with 1 characters in the string, you reach to this state. With 2, 3, 4, and with 5, you reach this. Now with any more characters, you should not be accepting the string, so it's just a reject state. And when does it progress? Well, with any kind of character, anything from sigma, whatever you want, it will progress, but it must consume 1 character at least. You cannot put an epsilon. I mean, of course you can't put an epsilon, it's a DFA, right? Okay, next is the length of W is at most 5. Okay, that's done. W is any string except 11 and 1 1, so except 1 1 and 1 1 1. So just make the complement of this, that W is only the strings 1 1 or 1 1 1. It's sort of like the, yeah, that would be probably easy to make. So it's, yeah, I guess it's gonna be easy to make. Right. You could do it in 2 ways. First, you could just think of the language where you have only 1 1 and 1 1 1, but then that's the union of 2 singletons, 1 1 and 1 1 1. So you just make a machine which accepts only 1 1, and with anything else it will just trash it. So over here, like, so we made a machine where, you know, it accepts a sub, if the string contains a substring, it accepts it, right? You could also make a similar machine where if it contains any more than the substring, it will trash it. So let's just say you have a substring A, B, C, D is whatever you have. You do the same thing. You have an initial state. With A, it goes to the next state. With B, it goes to the next state, and so on. But with anything else, it just gets trashed. Right? Actually, you don't even need to trash it in the end, because like if it's A and suddenly you encounter something else, what do you, okay, yeah, I guess you probably do need to trash it. Yeah, so in that case, you just say, well, we don't do anything. Yeah, like we just completely trash it. So I guess it's okay to draw another state, which is a reject state. So anything else, it just rejects it, but like finally, if you somehow do not get rejected, then you reach the accept state and you're done. And then with this, with like any alphabet, it just like loops back. Cool. So that's that. So just draw this machine with which accepts only 1 1, and then something which accepts only 1 1 1, and yeah. Right. In fact, you can even draw that in a single machine. But anyway, if you encounter something weird, you can just say, draw a machine which accepts 1 1, draw a machine which accepts only 1 1 1. Then, since we want the union of these 2 languages, make a machine which is the union of these 2 machines, and then make the complement of that. Just, yeah, it's getting pretty complicated, but whatever. Then you want W such that every odd position of W is a 1. Sorry, what? Every odd position of W is a 1. Right. So what about the even positions? I guess they could be anything. Right. So it's pretty simple. Like, so 0 is an even position, right? So okay, are we starting with 0 or what? If I have a string like, is this first character by 0th position or the, I think it's the first position, like, yeah. So it doesn't matter what the first position is, right? It could be any character and it gets promoted to the next stage. But and I just said this is actually the accept state. Like if the string was empty, we are already at the accept state, so we shouldn't be doing anything. But with only a 1 can you go back, right? So every odd, oh sorry, every odd position should be a 1, not an even position. So first position is an odd position, so this should be a 1, and then even position like doesn't matter, right? So both of these are like accept states. But so suppose over here, like you're accepting some kind of an odd position. If it's not 1, so if it's the whole sigma minus 1 thing, then you just reject it. Yeah, this looks okay. That's how the machine would be. Okay, this is getting pretty boring, right? Just go to the next one. Give the state diagrams of NA phase. So NA phase is slightly different because now your delta function is going from sigma cross q to a set of like states. So how do you write this thing though? The power set of q. Yeah. So set of states, and not just a single state, right? So I hope you guys know how NFA works. Fine. So these two A questions, I think these are like important, and everything else is not important. So we'll just do the first one. The language, the set W such that W ends with 0, 0, with 3 states. With 3 states. Okay, cool. So you should have 1 0 to go forward, you should have another 0 to go forward. Right, and this should be your exception because 0, 0 by itself should be a valid string, right? So that's, of course, it's supposed to be there. Now what? That's the question. If it's anything else, what should you do? Yeah. So there's, I'm not going to draw any kind of epsilon arrows because I don't want to. I think that's correct. Yeah. Okay, I could draw this thing like if, wait, why even draw that thing? Wherever you're like, you don't have the input available, you just like trash it immediately. So that happens in an NFA in any case, right? Yeah. Okay. So that happens, then what? What about the ones? How do you handle those? Well, in this state, if you encounter a 1, what do? You cannot, can you actually make it progress? No, but you can loop it back. You can always say, oh well, it tried. So you just loop it back, right? Hey, I'm drawing a DFA, it's not an NFA at this point. Right. And then you have a 0. Well, okay, what happens if you encounter a 1 over here? You can't like really say anything, but you can always loop it back for here, right? So you start off once again. Right. So if this has to end, you should just have this, right? That's the only way. So I get how this would work with a DFA. Then NFA though. Hey, so what was it like? Like, with an NFA, it's something like whether or not you take the input, right? No, the thing was you could have multiple arrows with the same label, as in, yeah, that's, so if you had a 0, you could, right, it makes sense. So this is actually a DFA. It's a DFA, but you could always say that it's an NFA as well. Yeah. I guess this works. Then the language of exercise 1 point, I don't know what that is, with 5 states. Okay, I don't know. The language 1 star 0 0 1. So I guess we'll be using a GNFA in that case. Yeah. So it's a generalized NFA, that is, with 3 states. Oof, that's hard. Okay, think about it. So one star is like you got any number of ones. So the initial state, like you don't even start, you just have bunch of ones, right? And if you encounter a zero, well, then that's probably coming from there, right? That's what you think initially. Yeah. So it's 0 0 and then you have 1 plus and that's starred. Oof, that's weird. So just first of all, what is 0 0 1 plus? It's a whole set. And then you're starring the whole set. That is to say, you're concatenating. Oh god, this is kind of complicated. So anything from that set a bunch of times. What is this saying exactly? So 1 plus is basically saying you should have at least 1 1. Wow, that's sort of rhymed. So you just have 0 0 1 0 0 1 1 0 0. Okay, yeah, all of that stuff. So you only need two zeros, right? You can only have two zeros consecutively. You can never have more than that. Okay, and you cannot have a single zero at all. Why do I feel that I'm in the end just going to draw DFA? Yeah, that's weird. I should be drawing an NFA. I should be drawing an NFA. Let's just try. So with the first zero and with the second zero, you progress to other stages, right? And once you are at that stage, any sort of one will just like send you back to the first state. So it doesn't matter how many ones you have, you just get back first state. Right. And I suppose the first state is also the accept state because epsilon would be a valid thing. Yeah. And you want with three states. Well, I did it. I did it with three states. It looks correct to me, at least. Like, unless you encounter a 1 over here, you cannot let go, right? You are trapped, sort of. So this feels correct. Like, okay, with at least 1 1, you once again enter an accept state, and then you have to loop over 1 a bunch of times because 1 plus is basically like 1 and then a lot of other ones. Sort of makes sense. So that's how it should be, I guess. Am I missing something? Yeah, I don't think I'm missing anything with this. Am I? No, it looks correct to me. But once again, that's just a DFA. It's not an NFA. Where do I use the fact that you can use non-determinism? Give me a hard question. So what is this one? Language 0 star 1 star 0 plus with 3 states. Why do I feel once again I'll be able to do it easily without doing anything complicated? So first a 0 star, okay. And then you want a 1 star. Okay, this is slightly different. And then you have at least 1 0. I think it might even be doable with just 2 states actually. So 0 star, so it doesn't matter how many like zeros you take, you are rested at the first point. With 1 star, if you take even a single one, oh wait, yeah, this isn't going to be in 2 states unfortunately, because you just have to have 0 plus. So there's a single 0, that's kind of complicated. Right, this has to be an NFA. Yeah, this has to be an NFA. I get it. This one has to be an NFA because, yeah, so the machine has no way of knowing that the first 0 it encounters, whether it's from the 0 star or whether it's from 0 plus, right? Yeah. And epsilon strings should not work, so the first state cannot be an accept state. But if the first state cannot be an accept state, just zeros looping back to it, that's kind of problematic because, right, like, yeah, you will have no way to progressing to the accept state if you're stuck at it. Like, suppose you just had 0 plus, right? You forget about this part for a while and you just had 0 plus, and the first state was the accept state. Well, and you're looping back to it with zeros. You are stuck, right? If it was a DFA, you would be stuck. But if it's an NFA, you have a choice. You are either stuck on first, or you could have two arrows with zeros, right? One where you loop, one where you do not, where you like go to the next thing. I guess, yeah, that's where the non-determinism comes in. So with a zero, with at least one zero, you go to this state to accept, and then you loop basically. With zeros you can loop. With anything else, you just trash it immediately. I guess that works. Right. I guess that's like an unwritten rule in NFA, right? That if the label isn't there for an arrow, then all you have to do is just trash the whole procedure, like kill off that branch. Yeah. Okay, so now you know what's going to happen with zero. Either you loop in the initial state or you loop in the final state. If you're looping in the initial state, that's to say that you are at 0 star. Then there must be a 1 star. So whenever you encounter a 1 for the first time, you move to this, right? And with every 1, you just go back to that. But once you encounter at least 1 0, you have to go to the final state. Cool. Yeah, this looks correct to me. So that's this language, 0 star, 1 star. So finally we were able to use something that that could not have been done directly. Right. So for the language F, what did we do once again? Yeah, we did this thing, right? So because epsilon strings would also be working. Cool. So the first step had to be the accept state. Right. Yeah, it doesn't look too bad to me at least. Cool. What about this one? The language with just an epsilon with one state. Yeah, so just have this. This is the initial state and the final state, and then you have an epsilon arrow. Anything else, it gets trashed immediately. I guess, yeah. Hey, but won't you stuck? Like, you'll never read the whole input in that case, right? I mean, okay, so once your whole input is read, that's when you start doing stuff. Like, that's when you start accepting or rejecting. So I guess this works. This works. Yeah. Okay, the language 0 star with one state. Zero sounds like just a bunch of zeros basically. So yeah, there's just one state, and with every zero you just come back to it. But if you encounter a 1 at any point, you are stuck. I guess, yeah, that makes sense. Then use the construction in the proof of theorem 1.45 to give the state diagram of any face recognizing the union of languages described in exercise 1. Yeah, I'm not gonna do any of that. Oof, concatenation of languages. State diagrams. So I'm just gonna do it for any general NFAs. Suppose you have, so once again, we're talking about concatenation, and this also works for DFAs. Suppose you have this N1 NFA and then N2 NFA. The concatenation works like this. Whenever your N1 ends, like all the final states of N1, they all must somehow lead to N2. Like, yeah, and that's why you have to have non-determinism over here, because these could go back in N1, right? Once you're at a final state, it could be that, oh well, N1 string isn't over, so you go back to N1 and then do a bunch of stuff. Or it could be that, oh, the N2 string is starting, right? So once you enter N2, there's no turning back. So whatever the initial state of this is, you just point to that. There's no turning back at that point. So once again, you got some of these final ones, and at that point you finally are done. Yeah. So that's pretty much it. That's the concatenation. That was a bit too easy, right? So the initial state is the initial state of n1. The final state are the final states of n2, and the total number of states are just the union of all of these. Right? So that's the concatenation. Fine. Then use the construction of in the proof, okay, to give the state of the integration star of the languages. Right. That's slightly complicated. The star of the languages, right? So you just have kind of the same thing. So you have an initial state, like if it's an epsilon string, well, you're done, right? But if it's not, then you should also have this thing. So your initial state in n1, it's linked to it by an epsilon string, right? So either you are done or you are starting. That's kind of weird, but yeah. So notice that with an epsilon string, you are at a final state, but you're also at the initial state of n1, which is by the way not a final state. And then you do some stuff in n1 or whatever your n is, and then these are the final states, right? You won't draw it like that. You won't actually draw it like final states. Instead, what you'll do is like you will loop it back to this with an epsilon. As in, once you have reached the final state, you could end, but there's a possibility that you go to the initial state once again. So yeah, that's probably the thing. That's a loop, sort of. So that's where non-determinism comes handy with concatenation and with this stuff. And since like the concatenation of two NFAs, that's almost like the concatenation of two languages, it is like that. And every NFA could be, so this by itself is also an NFA, right? So every NFA could be converted to an equivalent DFA. What we're basically saying is that there always exists a DFA such that it expresses the concatenation of two different languages, which are of course regular. Cool. Say diagram of NFA recognizing star of the languages. So that's for the star of the languages. What about for the plus of languages? Well, then this wouldn't be an accept state. Instead, you would have these as the accept states, right? Yeah. Cool. Prove that every NFA can be converted to an equivalent one that has a single accept state. I mean, yeah, come on, that's pretty easy. It's actually pretty easy. Like whatever machine you have, whatever NFA you have, you know that whenever it enters an accept state, there's a special label accept to it, right? So might as well make that special label a node and then say that, well, it just automatically gets transferred to this guy as well, right? Yeah. Oh no, wait, actually this might be complicated. Nah, it's okay, because whenever like it will take the next input, if it is at that, it gets trashed immediately, right? So it will never be able to complete the whole string. So yeah, that works with a single accept state. So I think with these these questions mark A, these are questions that we're supposed to be actually doing. Once again, an A question. Let B be a language over alphabet. Prove that B equal to B star if and only if B is in B. Huh? B is the same as B plus, sorry. Okay. Any language over the alphabet. Fine. So that happens if B is in B. I mean, the concatenation of B and B is in B. Yeah, okay, it's a subset of B, that is. But you kind of know that the concatenation of B is. Wait, what? So you're saying B is the same as B plus. That's weird. Okay, let me think about it. B is B. It's a subset of B. Okay. If it was equal to B, this would have been like done in no. It wouldn't be problematic, but it's a subset of B. So if B contains the epsilon string, then of course the concatenation of B and another like thing which contains epsilon string, that includes B itself. So then you would have to say that these two are the equal, like these two are equal sets. The only way this would happen, and then these are not equal, is if capital B does not contain the epsilon string. Right. How do I make this happen though? How do I make this happen? It's B plus. Come on. Think about it. No, it doesn't make sense. Like B is a set of strings and there may not be an epsilon string, right? And then you're concatenating it with itself a bunch of times, right? So for example, you could have B, 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 just so on. Let's consider two B's for example, and you know that none of these B's actually contain the epsilon string. So what would actually happen is like, okay, if this string is of one character and this string is of one character, yeah, I mean the one character strings, those are just vanishing, right? Those will never like happen to be there again, because like suppose you are a one character string in B, you have to combine yourself with something from B. The only way you could do that is like to give the smallest string would be with another string which is also one character, but then these two combined is just a two character string, so there will be no more one character strings in BB, right? You get it? So B equal to B plus would be stupid, because BB would never be like, this is very weird. Oh wait, no, sorry, B plus is not that. So B plus is this thing, right? B union BB union BBB and like so on. So of course it contains B because it already contains B, but the thing is like this is contained in B, so this whole thing is contained in B, but at the same time this is contained in B and this is contained in B. Yeah, you get it, right? You get it. This is a part of B, and that once again is concatenated with B itself. Now that's also part of B, because BB is a part of B. So yeah, it just goes on forever, and then you just say, oh, this whole thing is a part of like B. So like B plus is a subset of B, but then you know that B is a subset of B plus. So the only way is that these two would be equal. Okay, I get it. It's very weird, but yeah, I get it. Cool. So these A questions are nice, I suppose. I kind of feel guilty that I'm skipping all of this. Oh, 119 is good. Sorry, 1.19. Then you want to find a procedure to convert this regular expression to non-deterministic finite quanta. So you know it's a GNFA from the get-go. We're saying 0 union 1 star, 0 0 0, 0 union 1 star, right? So you can do it like this, that you can split it. So this is the initial, this is the accept state. Oops. That you split it into another GNFA which is something like this. Is one star. This is like 0 0 0. It progresses to this, and so these are just concatenated, right? Yeah, sure. But then this you can actually kind of split further. So with each of these zeros you go to a next stage. So 1 2 stages, first 0, second 0, third 0. So yeah, subsequent stages, and then you have 0 union 1 star. Cool. It doesn't matter how many zeros or ones you take. Oof. So just 0 union 1 is like this set, by the way, 0 1. Yeah. So it doesn't matter how many zeros or 1 you take, you get back to this guy, and that's like a star over there. So it could also be the epsilon thing. Yeah, you probably shouldn't be doing this in the first place. You shouldn't be doing it like that. You should instead be doing it like this, Similarly, this one you should be doing like that, and then this would be the accept state. So basically it's like 0 or 1. Sorry, so any 0 or 1, whatever you do, it gets back to this thing. And then you have these two states. So with a 0, with a 0, and with a 0 you progress forward. And this is the accept state, and it doesn't matter what you do now. It's like with any 0 or 1, just get back to this thing. So this is essentially saying like it contains a substring 0, 0, 0. And that's all it is, right? Yeah. So I guess we could do any of like these easily. Next thing. These are easy questions, but like there's a slight increase in difficulty every single time, and you don't want to be missing out on stuff. Convert these to regular. Come on. Fine. So how do you go from 1 to 2 with a b and then 2? Okay, this is kind of weird. To a regular expression. This already looks as regular as it can get. Oh yeah, so how do you do it? With the a, it gets back to itself. You don't want this loop. So what you do is like you do b a star over here. Right. So this whole thing could just be simplified to this. Like state 1 and state 2. With how many a's you want, well, it just gets back to state 1. So it doesn't matter. So with a star b, you get to 2. Right. And with a star b, you get to 1. Right. Okay. Yeah, I mean, that's how it should be. Hey, I think I've forgotten how to do it. What was the thing? What was the how do you used to do it? Yeah, you used to pull out the nodes, right? You just pull out any kind of node which is not an accept node or a reject node, something like that. Oh, right. So first thing you do is like you create a new accept state and a new reject state. So we call this state 0 and this is the state 3. You pass an epsilon arrow and then say that immediately you'll just go to the first state, and then you have this thing going on a, and then you have this b over there, and that's a b over there, and whatever. Oh wait, okay, no, also need a second state. So that's the b over there, this is the b over there. With a you loop back, and this once again with an epsilon goes to the final state. This is actually the final state. So now you actually start, right? First you want to delete this node 1. How do you do it? Well, let's just say you want to go from 0 to 2 because that's the only transition, and from 2 to 1 is also possible, but yeah, it's almost like if that was not there, something like that, right? So if you want to go from 0 to 2, how would you do it? Come on, think about it. Yeah, I mean you are supposed to be pulling out the node, but then there are incoming arrows and all of that stuff. Oh god. I get the algorithm I mean I get the gist of it, but actually applying is slightly harder, right? Yeah. This was a DFA, you converted it to a GNFA, and now you want sort of how do you do it? So you want to go from 0 to 2, because that's the only transition. 1 accepts arrows from 0, and it also accepts arrows from 2, I guess, and from itself, of course. but with 2 it can only go back, so that would be a self loop. I get it, because with 2 it cannot go back to 1, sorry, it cannot go back to 0, right? Yeah, so that's how you do it. So ingoing arrows, then the looping arrows, and then outgoing arrows. That's how you construct a path from 0 to 2. So this is what we are talking about, and this is not a final, except it's not a final state. We're talking about the number 0. Okay, so the way this will happen is like it will go to 2, but how? So first epsilon, which is nothing, then a bunch of times, so it's a star, and then with b. So that's how you get back to this thing. Now 2 can also go back to 2. That transition is there, by the way, right? You can never go back to 0 once you enter 1, but you can go back to 2. How does that happen? Well, you have an incoming arrow and then you have an outgoing arrow to 2. But then there's also this a stuff, so it does it like this. It's b, a star, b. Yep, that's how it happens. And then finally it goes to like 3. Oh, there's also this thing, there's the a over there. So you'll combine it and say, will this union with just a single a? Although at this point it doesn't matter, like it could be multiple a's as well, because it's the same thing. Yeah. And then we just have this 3. This looks correct, right? I guess this looks correct. Oof. Should it be union a star though? Yes, it should be. I mean, 2 goes back to 2 with either you have something from a star or you have something from this. Because with a it can only go back to 2. Yeah, it makes sense. And then is the final state, the state 3. So now it should be easy. It should be doable, right? So now from 0 to 3, which is also the final state, the transition is something like a star b is concatenated with this string. So this concatenated with b a star b union a star, right? And then you have the epsilon string, so that doesn't actually matter, and that's how it should be. Cool. So once again, a regular expression. Similarly with this, it's a 3-state one and you want to convert it to final state. Yeah, there's like 2 accept states, so each of these would be linked to the, so yeah, you get the thing. But still, let's just do it for practice. So you have a 0 state that's going to state 1, state 3, state 2. It's a and b, which at this point would just be the set AB. There's a over there. Oh, it goes back. Okay, now the states 1 and 3 were accept states, so they would be going to the final state now, the new final state. Let's call it 4. Right. Yeah, that's how it should be. And they go back with the epsilon string. Epsilon. Cool. So now let's just start locking away different things. So first I want to delete this node 2. So 2 is only like related to 1 and 3, there's nothing else going on. So yeah, I'll just do this. So I want to go from 1 to 3. What's the path that I should walk on? I should do either A or B, right? So this, I'll just like say it's A union B basically, because I want to use regular expression, so it's A union B. So I do A union B, I get to 2, then there's a loop, so just A star. So 1 to 3, it would be some kind of transition like this. A union B, then you have A star, and then you have to take a B, and that's how you reach 3. Now if I want to reach 3 itself from 3, how do that? I know how to go from 3 to 1. There's only one way. It's A, because from 2 you cannot go back. From 2 you can only go to places 3 and to 2, which we deleted anyway, so yeah, you can only go to 3 basically. That's only the possibility. So from 3 you can go to 3 itself, VR2 that is. So that happens with with a B, A star B. Cool. So now you have this thing. Okay. And it's connected to 4, which is the final state. And this is connected to epsilon. Once again, time to pluck out another of these states. And let's just say I want to pluck out 3 at this point, which is going to be hard. Yeah. Okay. So we'll have 1 to 4 and 4 to 1. That's the only transitions, right? Okay, so what happens with 1 to 4? How does that happen? That is, hey, wait a second, something's weird about this, right? Yeah, something is in fact weird, but what? Yeah, never mind. It will work out. I think. Wait a second. And if nothing else, you can always add another state in the end. So just deal with it for now. Right. So going from 1 to 4, how does that happen? Well, you're plugging out 3. Okay. So it could either happen with the epsilon string, because you can directly go to 4, or so you have a union, or you could do all of this stuff. So it's A union B, A star B first to get to 3. Then you have B, A star B multiple times, right? So that starred. And then you have an epsilon. So it's going to be a handful to write down. A union B, A star B, right? And then you have what is this thing? Yeah, B, A star B starred, and then an epsilon string. So that doesn't do anything. So that's how you go from 1 to 4. And you also want to go from 4 to 1. How does that happen? This should be the forward direction. This is the reverse direction. So the reverse direction happens as so this is like in this direction. Wait a second. Is there a reverse direction? Okay, there doesn't seem to be a reverse direction. Oh, I missed an essential part. You can always go from 1 to I get it. No, okay, I didn't miss it, I guess. So 1 to 4, that's the only transition, right? 4 to 1 is not possible. Yeah, because from 4 you cannot ever reach any other state. So this is not there, this arrow is not, so it's going correct, and then the transition that should be there is 1 to 1 itself. So how does that happen? That happens as this thing, A union B, A star B, that stuff, then B, A star B starred, right, and then A. So that's how you reach back to 1. Yeah, okay, that looks about right. Let me just think about it for a while. Yeah, okay, it's correct. It looks correct. And then with this 0, you just reach that and with that. So now it's very much doable. So you get a very messy and big regular expression, but it's okay. So first you do epsilon, then you have to do this a bunch of times. So there's a star over there, so that already has the epsilon in there. Yes, and so that concatenated with this thing. Oof, come on, think about it. Oops, where did it go? Yeah, it's okay, it's gonna resize it. I'm getting the hang of it. So the final expression that you'll be getting is A union B. My handwriting is bad. A union B A star B, B A star B starred, then an A, well, this whole thing starred, and there's a good reason for that, because this A has to be there at least once and all of that stuff, right? And then you have this stuff, so epsilon union this union A union B. Oof, what is this? A star B, and then B A star B starred. Wow, there's some messy stuff going on. But yeah, that's pretty much it. So this simple looking diagram got converted to whatever this is. I don't like it. I certainly don't like it. Shouldn't there be a way to simplify all of it? Let's concatenate with that. I don't think there's a way to simplify any of it at this point. Come on. Hey, so both of these start with an A union B, right? You notice these two are like very similar looking expressions? I guess I do. At least I do. It's basically just this expression and this expression. Like, it repeats, but there's an A in between all the time. So these two expressions are like delimited with an A, sort of. And you could end it at an A, or you could put another of these expressions. That's pretty much the thing, right? Yeah. Okay. I get it. It's weird. That's all I can say about it. Fine. Next. Then you have this thing. For each of the following languages, give 2 strings that are members and 2 that are not members. Okay. Yeah, I'm not doing that. Next question. Certain programming languages, comments appear between delimiters, such as, right? Let C be the language of all valid. Oh God. Sorry. The hypothetical language C be the language of all valid delimited comment strings. A member of C must begin with this and end with this, but have no intervening hash star hash slash. For simplicity, assume that the alphabet for C is this. Okay. Give a DFA that recognizes C. It's pretty easy. I'm not even going to do this. Lots and lots of questions. Right. So what are these star questions? I guess these are the tough ones. Fine. Let's just do this A. Let B and C be languages over sigma equal to 0, 1. Define what? Is the set of W contain W in B for some Y in C, strings W and Y contain equal number of bonds. What are you doing? Okay, so these are N2 languages. Fine. Then you're talking about some language where W is in B for some Y in C. Okay, such that for some Y in C, strings W and Y contain equal number of points. As in, yeah, just find the digit sum of, we could call it that, of W and the digit sum of Y, they would be equal, and there exists a Y in C such that this would happen for all W in this new language that we're defining, which are by the way also in B. That is, show that the class of regular languages is closed under this operation. So essentially what we want is that this new language is also regular. Okay. Come on. Suppose B and C are regular languages. think about it. The equal number of ones. Every one you essentially do something and you have to reverse that with some y such that it contains equal number of ones. What is this? Come on, think about it. Class of regular languages is close to this operation. Okay, it's hard. This one is pretty hard. Just that it contains. So could you make a machine that recognizes this language? That's a good question. What about a regular expression? Could this be expressed as a regular expression? Like you have a language B, then anything from that language. Right. There exists a Y in C such that the strings W and Y contain the equal number of ones. Why would that be a regular language as well? Okay, so it's something like it doesn't even matter what Y you have. All you want is like with C, right? This language, you have you can construct a set which contains the number of ones in any particular Y in C, right? So this set can contain like 0, 1, so on, all of that. So then you just want to cherry pick from B all the everything that contains 0 zeros and then 1 ones and then so on, right? And if this kind of list is finite, well, we are already done. If it's infinite, then it's complicated, and it probably can be infinite. Okay, think about it. What if you just had to do this thing like B, but all the words that contain only 0 ones, right? Then essentially you would be thinking of a language which does not contain, like which contains only 0 ones, something like that. Okay, consider this language 0 star 1 0 star. Think of it as a unit, right? And then think of this starred, then you have 0 star. Oof, okay, it's kind of not starred, it should be the power of n. Yeah, and then you have any number of zeros. I mean, those are already there, so you don't have to think about it. It's n, you say. Yeah, that seems about right. So this regular expression gives you a language which contains, by the way, you don't even need the 0 star, do you? What if it's just a 0? Well, then it's like problematic, so you actually do need it. I guess you can remove this, by the way. Yeah, because you already have enough number of zeros already, right? So this is the thing. This language, also going to say, yeah, this language contains it's a set of all strings such that it contains exactly n ones, right? So essentially, if you want all the strings in B such that it contains n ones, you just take the intersection of this thing with B, and you know that regular expressions, regular languages, the intersection of those, that's like, the intersection of regular languages is also a regular language. So this would be a regular language, but then similarly would be like, it's gonna be for every single n value, right? And then you just combine all of that using a union operator, and that's supposed to be a regular language. But the only problem with this is that the finite union of regular languages is also a regular language. Once you have an infinite union, it's complicated. For example, consider this 0, 1. Actually, just start with epsilon. Consider this union. It's the union of 0 power n, 1 power n, these strings. I mean, it's a set containing these strings. Simple singletons are, by the way, of course, regular. And then is from n equal to 0 to infinity. This union is problematic because it's not a regular language anymore. The pumping lemma doesn't hold for it. Yeah, so wow. Now what? Yeah, I mean, now what? This doesn't work. Oof. So is it closed? They told me that it's closed. We have to prove it. Come on, think about it. Even the complement of this set, like, that could be infinite, and it's also messed up. I actually do not know how to do this. Contain equal number of ones. Could there be no way of doing it? If that's in the set, then you're done. Oof. How? How do you make sure that the number of the digit sum of that is in the set? This also in the language. If this is a finite set, we are essentially done. But if it's not, it's complicated, right? If you could find a counter example, we would be done, right? Well, this is also a regular language, isn't it? Yeah, it's a regular language. Sure. So what does that mean? Hey, wait a second. Just wait a second. Is it that, this set is some sort of a special set, like it has more restrictions on it? It could be. It could be. Come on, think about it. Like maybe the gapping between these is like regular or something, or there's some pattern or something like that. I truly do not know how to do this. Yeah. How would I make sure this actually happens? No, I do not know. I have to search this. So I'll just not do this question for now. This was tough, isn't it? Okay, so there are even more weird operations that they're defining, and then they're saying that, oh god, vectors. Seriously. Now you have vectors associated in. No, these are problems. And these are just like, it's just all exercise. I get it now. This is what I should have started off with in the first place. So I guess I'll take a break for now and I'll continue it. So see you guys in the next video. Bye.